Welcome to our effects course for MPM Fundamentals. I'm Eduardo Besril. In this course, we will go over the new MPM Solver available with Houdini 20.5. We'll begin by creating our simulations using the pre-configured and manual setup of the MPM Solver, as well as going over the things that you should be aware of while creating your simulation. The goal of this course is to introduce you to the concepts of MPM and how it differs from other solvers. MPM stands for Material Point Method, and it works as an extension of flip to solid mechanics. The main takeaway and difference from other solvers is that MPM is efficient for creating big chunks of different materials and mixing them together. If you want to do these things without MPM, you will have to pick and change different solvers to get similar results. Unlike Vellum grains, for example, MPM doesn't have constraints as it works more as a continuous material. And if you are unsure of which solver to use for your simulations, keep in mind that MPM leans more towards creating solid materials and is capable of simulating small-scale fluids. Now, there are some things that you should be aware of when using MPM. The first one is that the solver does substeps dynamically based on the stiffness and resolution of the material. By default, you will start with the lowest amount of substeps possible, but you can also change the values to your liking. Speaking of liquids, MPM does allow you to create small-scale fluids as it oversamples the source, which allows you to have tons of particles. But just keep in mind that you won't have surface tension while creating drip effects. If you are maybe thinking of doing a big water scene that is not colliding with other materials, then it's probably better to stick to the flip solver. Now, there could be a misconception that you need to have some knowledge of vellum grains in order to understand how MPM works. But even though there could be some similarities, they both do their own separate things. You can easily start to play with MPM even if you've never touched vellum grains before. Before diving into Houdini, let's take a look at how the MPM setup will look like in our scene. On the far left, we have our MPM sources. Here is where we'll define the behavior of the geometry. In the middle, we have our MPM collider, which can either be a static or dynamic geometry. If you choose to use a dynamic geometry, you have the option to manually animate an object or use an animated character. What the MPM collider does is that it converts your collision geometry into a VDB. You can have as many geometry objects as you want in both the source and the collider. And then on the far right, we have our MPM container. Here is where we drive the resolution and boundaries of our simulation. Keep in mind that the resolution of the source and collider is driven by the resolution of your container. As for the solver itself, this is where we control our substeps with the CFL and material conditions along with our ground plane. Now that we have these concepts, let's jump into Houdini and build a scene using the MPM Configure setup. Now that we're in Houdini, let's take a look at how the MPM Configure works. You can start by creating a geometry node, and we can name this MPM Configure. Dive inside and type MPM. Here, you can see that we have a lot of options to choose from, and these ones at the very bottom are some examples that showcase the different types of materials and setups you can create with MPM. But for now, we're going to go over the MPM Configure. This MPM Configure setup shows you how your node tree should be wired together, and if we hit play, we can actually see that it's already working. Let's go over the nodes and see what each of them is doing. First, we'll go with the MPM source. Here, we can see that we have a sphere that is working as our source. Here in the MPM source node, you can see that the first thing that is asking us is for our MPM container, which is actually going to be this one over here. Remember that this container needs to be linked to both your source and the collider, as it's going to drive the resolution of both of them. Here we have our emission type set to once, and if we hit play again, we can actually see that it's only emitting our material one time. If you want your material to be continuously flowing, you need to change the setting to continuous, and the slider needs to be active on 1. If you move it to 0, it will become inactive, and if we hit play, our material is going to be continuously flowing. Now, here is where we set our materials. Right now, by default, our MPM is behaving like snow. But if we change it to something different like water, for example, you can see how our particles are going to behave like water. Keep in mind that not only the behavior of this is changing, but also the parameters and attributes of the material. I'm going to go up and change my emission type and set it to once again. If you'd like to, you can also add an initial velocity to your particles. I'm going to add some velocity on the x-axis, and when I hit play, my particles will be thrown to the side. Now, let's go over our MPM collider. Here, we have a box that's working as a collider for our particles. You can see that it's asking you for an MPM container, which is actually going to be the same one as the source. Now, what the MPM collider is doing is that it's converting this box into a VDB. Next, we have our collider type, and this can either be static or animated. Notice that there are two types of options for animated, which are rigid and deforming. If I drop transform node, and I decide to write an expression to animate the rotation of this box, we will have to change the collider to be animated rigid for it to work. And if I hit play, you can now see that our collider is actually moving. The second option is animated deforming. This is useful for when the point positions of your geometry are changing in relation to each other, such as with a character mesh. Now the container is driving the resolution of the collider and the MPM source. So if I go to my container and I change the particle separation to 0.01, you can see how both of these have a better resolution. However, if you want to adjust the collider's resolution independently, you can go to the collider and check this box. So if I put a value of 0.05, you can see how it is only affecting the collider. And even if I change the resolution of my MPM container here to something like 0.09, you can see that only the source is the one that's getting affected. Finally, we have a friction and sticky parameters, which control how the particles interact with the collider. A low friction will cause the particles to slide, while a high stickiness will make them stick to the collider. You can tweak these settings to get the interaction effect you want. Let's go over our MPM container. This is where we will set the boundaries and resolution. As we previously saw, the resolution is determined by the particle separation. Every time you reduce this number by half, the resolution increases by a factor of 8. Additionally, you can set boundaries in your simulation. In the domain settings, you can adjust the size of these boundaries. You have the option to affect all boundaries at once or independently. If you want to select all of them, you select this checkmark, and then select close to actually see them. Be aware that when you select close, it will make the boundaries to behave like collisions. So for example, if I put a velocity of -20 here and then hit play, you can see how my MPM particles are going to be crashing to the wall. But if you select the other option, which is delete, the particles will disappear once they hit the boundary. And like in the MPM collider, you also have a friction and sticky parameter to play with. Now, let's go over to the solver. The timescale controls the speed of your simulation. A lower value will make the sim to go slower. The CFL and material condition determine how many substeps are created per frame. Reducing the CFL increases the number of substeps, but if you reduce the material condition, it will affect the stiffness of your material. If we go to our geometry spreadsheet and then we go into the details tabs, you can actually see here that we have our substep count. And if I hit play in the simulation, you can actually see how our substeps are changing dynamically per frame. Here, we also have our global substeps. This one actually refers to the DOP substeps. You will only need to adjust this value if you are experiencing substepping while having a continuous emission from your source. Additionally, the solver includes the setting for forces and your ground plane. Now that we understand the function of each node, we can start applying them in practice. Now that we know how the MPM nodes work, we can actually create our own manual setup from scratch. For that, we're going to create a new geometry node and we're going to call it MPM manual. And for this, we're going to dive inside. I already have some stuff ready so that we can get ahead going. Here on the left side, we have some USDs that are going to work as our geometry for our MPM source. And here, I actually have them merged so that we can see all of them at the same time. Now, what we're going to do in this exercise is that I want this capybara to actually start walking on my sources, but I want him to start walking below the ground as soon as he starts reaching this point over here, which is the middle of where our sources are going to be mixing. For this, we need to change the animation of the capybara. First, we need to add a motion clip, which we're going to connect to the third input, which is going to be our animated pose. Then we're going to do a motion clip extract. For this one, we're going to be extracting the main joint of our capybara, which is going to be this one. And the output mode, we're going to select it to motion trails. Now, you can see that this blue line is the whole animation of where our capybara is going to be walking from. But we actually want to go to the end and we're going to select the last point because it's the one that we want to transformate. So first, we can write a soft transform. And here in the group, we're going to select the last point and we can hit enter. And then we can translate its position on the negative value on the y-axis in order for it to start moving down. But we want this to actually be on our number 3, which is where he's going to be start to walking down. So for that, we're going to go to our soft radius and we're going to increase it until it reaches that point. Somewhere over here is probably going to be fine, maybe a value of 11. Then we can add a motion clip update. What this is going to do is that it's going to update the transformation that we did on this animation to the original. And then in order for it to change, we need a motion clip evaluate. And we can connect the first input here and then the last one over here. And now if we view our animation of the capybara, he's going to start going down as soon as he starts reaching this point. Now let's go over to our sources. For our first source, we can type MPM source. And if we actually display it, you're going to see that it's going to give us an error because we don't have our container. So for that, we're going to type MPM container, and we're actually going to plug this input into our merge geometry. And then if we just go to our source and we just drag and drop this one, now the error is going to disappear once we view it. And for this, we can actually just duplicate our sources. So this is going to be for my second source, and this is going to be for my third source. I want my sources to have a different material and behavior. For that, I'm going to go to my first one, and I'm going to go to select the material to mod. Because my capybara is going to be working on this one, I actually want his footprints to be visible. And for that, I'm just going to increase a little bit of the plasticity. My second source, I want it to behave like mod, but I wanted to change the behavior to be a little bit more like liquid. And I'm actually going to increase the density to a value of 2500. And then for my last source, I just want this to behave like normal water. Now, I can grab all three of my MPM sources and merge them together. But in order to actually tell a difference, I can actually add a color node to each of them. So this one can actually be something like a little bit brownish. And then the second one, it can be to something more greenish. And then the third one, I can actually just select it to something like blue. This is not necessary, but it just works as a better way to visualize your sources. And then after that, I'm going to drop my MPM Solver, and I'm going to connect my merge to the first input. Now, I need my capybara to actually be as a collision, so for that, I'm going to type MPM Collider. And remember that if I view this, it's also going to ask me for an error because we don't have our container. So for that, I can also just drag and drop it. And remember, I need to change the animation to animated deforming. One thing that I want to do with my capybara, and I'm just going to display it here, is that I want that once he reaches this point, I want the stickiness parameter to be in a value of 10 on the first frame. And as soon as he starts reaching the water, which is around this frame, I want the stickiness value to drop to 0 and the friction to be 0.01. And now with that, I can actually just put this as my collision. And for the third input, I'm going to connect my container. And if I view the MPM Solver, now we have our sources and our collision. But we can actually see that there are some particles here that are missing. And that is because of our ground plane. For this example, I'm just going to lower it to a value of minus 0.08. Now, our particle separation is quite low. So for this, I'm going to increase it to a value of 0.006. And before I do that, you can actually see how the distribution of our particles is going to change. And finally, in our container, I am also going to close all of my boundaries. This will make my particles to only exist in the area where the merge is. So when we start the simulation, they don't fall to the sides and only exist inside my container. Now I am ready to cache the particles. In the next example, we're going to see how we're going to isolate and mesh each of them. Let's take a look at how our MPM simulation looks so far. After the cache was done, I created a play blast. If I hit play, you can see how our three materials are mixing and interacting with each other. And now that we have our cache, we need to isolate each of the sources to mesh them. In order to isolate the sources, we need to add a blast node and we need to type the source name of each of the sources. You can find the name in the geometry spreadsheet in the points tab. And here you can actually see that we have all of our sources. We can right click and hit inspect, copy and paste the source name, and then head over to our blast and type @source name equals MPM source mesh 0. And we need to select our group tab to be in our points. And then if we delete non-selected, you're going to see that we're going to have our first source isolated. And we're just going to repeat this pattern for the next ones. We're going to do second source, which is mesh number 2. And then for the third one, it's going to be mesh number 3. And I can just name this isolate viscous, isolate liquid, isolate water. Now, here comes the meshing process. But be aware that there is no official solution yet to actually mesh your MPM particles. This is just one of the ways that you can do it. We're going to type a VDB from particles. In order to know which voxel size is appropriate for our simulation, we can actually use an expression to calculate the voxel size based on the resolution of the MPM. This expression is the next one. We're going to type detail, open parentheses, up, input path, open parentheses, quotation, dot quotation, comma 0, close parentheses, comma, the attribute dx, which stands for the voxel size, comma 0, close parentheses, divided by 2, divided by 1.51. So what we're doing is that we're going to take the voxel size for the first input of the node and we're going to divide it by 2 and by 1.51. The reason why we are dividing by 1.51 is because we need to make sure that the p-scale is 1.5 times larger than the voxels of the VDB, which is necessary to meet the conditions in the minimum radius in voxels. And then we can hit enter. Next, we're going to do a VDB reshape SDF. And we are going to change the offset to a value of 0.5. Then we're going to use a VDB smooth SDF. We continue with another VDB reshape and we are going to copy the offset parameter of our first VDB reshape and paste it as a relative reference. And we are going to change our operation to erode. And then with a convert VDB, I'm going to convert it into a polygon soup. When meshing MPM, it is recommended to always convert your VDB into a polygon soup, as you'll save memory and time, especially for larger geometry. The polygon option is more useful if you'd like to edit or separate your mesh. In terms of the meshing, we're actually done, but we want to add also a UV attribute to this mesh. For creating our UVs, we're going to start with a time shift in order to have our static mesh on frame 1. We're going to write a UV texture and we're going to select the attribute class to be on the points. Now, we're going to add an attribute wrangler. What we're going to do is that we're going to transfer the UV attribute from the static geo into the deforming one. The expression goes like this. We are going to take our UV attribute from the corresponding point number from the second input. And then with an attribute transfer, we're going to transfer the UV attributes from the points to the polygon mesh. Go to the conditions tab and increase the maximum sample count to a value of 100. Now we have meshed our MPM particles and added UVs, so it's ready for the rendering stage. We can use the same technique to mesh our second mod source. We can just drag and drop it and connect our nodes to the correct inputs. With this, our second source is now meshed and with UVs. As for the water, the only thing that we need to do here is that we need to add a particle fluid surface. Similar to the meshing of our VDBs, we are going to use the same expression. The only difference is that we will only be dividing it by 2. We're going to write detail, open parentheses, up input path, open parentheses, quotations, dot quotations, comma 0, close parentheses, comma, the attribute dx, comma 0, close parentheses, divided by 2. Now, our water is also meshed. One thing that we need to change is that we need to convert the output to a surface VDB. The final step is to convert our water into a polygon. So we use a convert VDB and we select polygon soup. So now our water is ready to be rendered. One extra thing that we can do that is not necessary but it adds an add detail to your render, you can add another particle fluid surface and you can set your particle separation to a value of 0.01. After this one, be sure to convert it to a surface polygon. Then you can create a VDB from polygons and change the distance to FOC VDB with a value of 0.01. The reason why we're doing this is because the first particle fluid surface is going to work for the mesh of our water, and the second one is to create a density that will work as the interior for the water, which is going to give depth to it. With this, we can just grab a null and name this out density water. All of our MPM particles are meshed and ready to render. You can add a file cache to each of them before sending them to Karma. In the next video, we're going to see the same example with a higher resolution to see how the particles ended up mixing and how the render looks with a very simple shading. Once our caches are done, we can prepare our sources for rendering by sending them to Karma. We can begin by switching our desktop from build to Solaris. And here we can actually type a loop network. And once you drop it, you can double click to go inside of it. We will import our capybara and the 3 MPM sources and then apply a basic material to each of them. But before importing them, I'm going to start by creating a dome light and I'm going to use an HDRI. For that, we can type tab and type dome light. And here in the base properties, we can go to texture and select this icon over here. From here, you can go into your file browser and select your HDRI. We can start to import our meshes. I am going to drop a sub import and I'm going to import my first mod source. Here in the subpath, I can click on the operator and go to my manual MPM geocontainer. I put a karma at the end of my nulls to distinguish the ones that are going to my render. For my first mod source, I can select viscous mod karma. Once I toggle the display flag, I should be able to see my first mod source. For the sublayer style, you can change it to the merge sublayer, and here in the import path prefix, we can delete the $OS and we can create our custom path. In this case, I'm going to create fx/viscous, and if we go to our scene graph path, you can see how we have our effects, and inside we have our viscous source. I can also rename my sub imports to viscous mod. We will repeat this process for our other sources. I'm going to drop another sub import, and I will import my second mod source, which is my liquid mod for karma. We're going to change the sublayer style to submerge and create our custom path, which is going to be fx/liquid, and rename my sub to liquid mod. Now we have our second mod source. Let's do the same for the water. We're going to do a sub import, select our water for karma, merge sublayer, and our path will be fx/water, and rename the sub import to water. Now we're just missing the density. Again, we do another sub import, select our density for karma, merge subpath, and change our path to fx/density. And we will rename the sub import to density. We have all of our sources imported. Now we need to add our materials. So I'm going to drop a material library. Double click to dive inside a node, and for creating our materials, we need to drop a karma material builder. This node will allow us to create our materials either from scratch or by applying textures that you created yourself or you downloaded it from the internet. For this example, we will see how to add some textures using the Material X image, but we will not go deep into it, just enough to give you an idea of how to apply textures. We can name our first material to water. Then we can duplicate this and rename the second one to our viscous mod, and the third one for our liquid mod. For the density, we need to drop a different builder, which will be the karma pyro material. We can change the name to density. Let's start by creating the materials. For the water, it's going to be very basic. I know I want the colors of the water to be brown, so I'm just going to play with the colors until I see something to my liking. This type of brown should be good. I can play with my roughness and drop it to a very low value, maybe something like 0.008. Then I can go to my transmission and increase it to a very high value. This will make the water very transparent. Now let's switch to our viscous and liquid mod. I am going to open this pane over here to select my base color. I can select the input and hit tab and type MTLX image. This will allow me to add a texture to my base color. I can select the folder icon over here and import the texture from my file browser. Then I want to add some displacement, so I can add another MTLX image and I can connect it to my displacement over here. So I just drag and connect this one. The only thing that you need to change is the signature. Instead of color, we're going to change it to float. And here, I'm just going to look for my displacement and apply it. Here in the Material X displacement, the scale is way too big. So for this, I'm just going to reduce it to a value of 0.01. Now, let's go to our liquid mode. Because this is supposed to be wet, I'm going to use a different texture. For this, again, I'm going to go to my base color. And also, instead of doing the MTLX image, I can also go to this color parameter over here and selecting the gear icon. And if you select texture geometry, you can select MTLX image and it will come connected to the base color. I will go again to the folder icon and select my texture and import it. I can also differentiate this by naming it base color. I can do the same for the displacement by selecting the gear icon next to the displacement parameter, and I can select the MTLX image. And the signature is already set as a float. I can go to my folder again and select my displacement texture. Let's now create the material for our density. Because the density is working as the interior of the water, I want the density scale to be high. I am going to select the value to 100. And for the smoke color, I will go with a dark brown. And for the absorption color, I will go with a lighter tone. All of our materials are ready, and we can now click on Autofill Materials, but they haven't been applied to our geometries. For that, we need to click on Assign to Geometry. And here, we can use our path prefix to assign the material to the corresponding mesh. For the water, it will be /fx/water. We will repeat this process for the rest of them. For our viscous mod, it will be /fx/viscous, and for the liquid one, it's going to be /fx/liquid. As for the density, it's going to be a bit different. We're going to do /fx/density/ and we need to select volume number 0. Before I display my materials, I just want to check that the scale in my displacement is low for both my mod sources. For the first one, yes, the value is 0.01. And for the second one, I will drop it to 0.01. In case we didn't switch this value, the displacement is going to be huge. And if we now display the material library, our textures are now applied to our sources. For the final step, we need to import our capybara into the scene. For that, we need to go back to our manual NPM and display our capybara. You can write a null and name it out capybara in order to identify it. And now, we can go back to our LOP network, and we can drop a scene import all. This will import all the geo containers that are displayed at the object level. And if we display it, our capybara is now in our scene. One thing that I want to do is that now I also want to add a camera. So first, I can move over the viewport and position where I want my camera to be. So for example, maybe I want it to be somewhere over here, and I can just select Control and select this camera button, and now my camera is going to be over here. The final step is that we're going to drop a karma node. So for that, you can type karma and just select the first option. This is going to drop both a karma render settings and a USD render raw. In the camera render settings, you can select your resolution for your camera. In here, I'm going to change it to manual, and the resolution, I want it to be 1920 by 1080. And in the engine settings, I'm going to change it to XPU. I'm going to go to my camera effects, and I'm going to enable velocity blur. And finally, I'm going to go to image outputs, and in the filter, I'm going to select for the denoiser the NVIDIA Optics denoiser. Once we have this, you can display the node and change the perspective to Karma XPU. And here, you can see how our scene is going to look in the render. You can move in the timeline to see how this scene will look at a different frame. You can freely move over the viewport and you can see how your scene is going to be rendering on real time. Because of this, you can see how your materials would look like in the render, but you can go back and edit them in the material library and tweak them to your liking. And before exporting them, you can select your output picture and select the camera that you want. In this case, we want to use our camera number 1. Once that's done, you can go to the USD render raw and select in the valid frame range, render specific frame range. Once you're ready to render, you can select render to disk. Before rendering, I went back to the scene and increased the particle separation to a value of 0.0034, which gave me a total count of 41 million particles in the scene. When doing NPM, Keep in mind that it is recommended for your scene to have between 40 to 80 million particles. And once the render was done, this is how the scene looks like. You can see how our particles are mixing and interacting with each other. If you wish, you can also make more tweakings to the scene, such as doing wet maps or changing the materials in the sources as well as the collisions. This concludes our MPM Fundamentals course. The scene file, complete with color-coded notes, will be available for download. If you wish to dive more into MPM, you can check out the MPM masterclass conducted by Alexander, as well as the snowplow scene by Lucas Albino in the SideFX website. If you have any questions, feel free to contact the Education Department at SideFX. Thank you very much.